Yes, sir, I'm doing good.
All right, let's cover reduced echelon matrices, or reduced row echelon matrices.
Yes, sir.
All right. Let me think how to explain these. When you have three equations and three unknowns, as in the problem
Yes,
on
sir.
the top left, you know that you can multiply both sides of any equation by a constant, right?
Yes, sir.
You can also add or subtract any two equations.
Yes, sir.
You can also add or subtract any two equations and take the result and replace it with in place of one of the original equations.
Okay.
Okay, so you
what allows that?
Go ahead. I'm sorry, what?
What allows you to be able to?
Well, first of all,
yes, sir.
Yeah, you can. We do it if you solve a 3 by 3, in other words, three equations and three unknowns, the normal way, by elimination. How do you do it? You end up by creating equation 4 and equation 5. And equation 4 is always the sum of two of the original three. And equation 5 is always the sum of two different of the original three.
Yes, sir.
Okay. So that's the essence of solving a system of equations by substitute or by elimination. Is all matrices do is matrices eliminate the variables. In other words, if let's just go through some of these steps. I'm trying to figure out what the best way. Let me try writing real small, because there's a lot of writing to be done here. So I am going to make this matrix look like this. Can't write that small. I'm just not physically capable of it.
Okay, so you're putting down the coefficients.
Exactly. And then I'm putting down the constant.
What does that line indicate that you just put in between them?
It indicates that we have an augmented matrix. That's what it indicates.
And an augmented matrix
has that line in it. Which are basically the coefficients and the constant of any system of equations.
Okay.
Okay. Now, here's the goal.
Yes, sir.
The goal is to take that matrix and make it look like something where there's a 1 there, a 1 there, and a 1 there. And that has to be a 0, that has to be a 0, that has to be a 0. And once you get it looking like that, whatever shows up over here, let's call it A, B, and C by the time we're finished, then Z is equal to C. Now, because once you get zeros on the left and you've got diagonals are all ones, then Z is equal to whatever that C is. Now, there's two types of these matrices. One where you still have numbers right there, and I thought my terminology was correct, but I'm not sure what the correct terminology really is, but this is what the matrix would look like. Where you have zeros everywhere except along the diagonal. Now, in this case, x is equal to x. And I shouldn't use x, y, and z. And let me use 3 different variables. In other words, if I can manipulate my original matrix and get it to look like that, then I know that x is equal to E, y is equal to D, and z is equal to F.
Because the ones represent the X, Y, and Z.
Yeah, and you not only have to have that, but you have to have everything else equal to 0. In other words, this is the perfect thing. If you use your calculator to do this, you want it to be like this. If the calculator is doing all the work, you want it to be whatever that's called. I thought that this was called a reduced row echelon. But in looking at my book, I don't think that's the correct terminology. But we'll get to that. The terminology really doesn't matter for the moment.
Yes, sir.
Okay? So if I can get it to look like that, I have my answer instantly.
Yes, sir.
The problem is it takes a lot more effort to get it to look like that than it does to get it to look like that. In other words, let's put some numbers there. Let's put a 2 there, and a 3 there, and a 4 there.
All right.
Okay. Now, it's extremely valuable to get it to look like that because the solution z equals c is obvious.
Yes, sir.
And now I know that 1y plus 3z equals b. So as long as I have a number in place of b, I can now solve for y quite easily. And once I solve for z and y, it's just a question of plugging it into that row, and you'll solve for x.
Oh, yes, sir.
So this is quite valuable. In other words, when you get it to that step, you're basically done. You don't need to do all the additional work, if you're doing it manually, that is.
Okay.
You don't need all the additional work to get it to the perfect. It's just ones and zeros. Now, let's talk about how we do all of this.
Okay.
Okay? Because this is really the essence. Okay, I'm going to do it this way. I'm going to label this so we can follow it. That's row 1, row 2, and row 3. Well, let's see. I already have a 1 where it's supposed to be, right?
Yes, sir.
And I have a 1 where that's supposed to be. So that's all I got to do is take this negative 1 on the bottom left and the 2, turn those into zeros, and I will have made a lot of progress.
Yes, sir.
So how am I going to do it? First step is I'm going to add row 1 plus row 3, and I'm going to replace row 3 with that result.
Yes, sir.
Okay, so if I add 1 and 3, the only one I'm replacing, I'm just going to leave row 1 the same. I'm going to leave row 2 the same. But row 3 is I'm going to add 1 and 3, which makes that cell 0. And that's one of the things we're trying to accomplish, is turn that cell into 0.
Yes, sir.
Now, what else do I get? I get 1 and 3. This turns into a 3. See that?
Yes, sir.
And I'm adding 1 and 3, so this turns into a minus 3. And I'm adding 1 and 3, so this turns
into a 0.
Yes. Excuse me. My dog's barking distracted me for a moment. Okay. Now I want to take that and turn that into a 0. I know eventually I got to do that even on a row echelon matrix.
Yes, sir.
And at some point I'm going to need to turn that into a 1 if I can. Now, the reason I say if I can is because they didn't really start us with an easy problem here. This is a hard problem. In other words, they started us out on the expert slopes, which I don't particularly like when I'm trying to teach something to somebody. I would have preferred they give a matrix that has a unique solution, but they didn't. It's okay.
Okay.
Let's go to the next step. Okay.
Yes, sir.
Now, the next step, I'm trying to turn that into a 0.
Yes, sir.
So, what's a good way to do that?
We could multiply row 2 times 3 or times -3 and then add it to row 3 and put the answer in row 3.
But notice the problem with that. That turns that term into something other than 1. So this is very tricky.
Oh.
It's not real easy to do these. You have to, it's like a Rubik's Cube. It really is. Let me go ahead and tell you what I did. And there are more than one way to do these things. I'm going to multiply 2, row 2, by -3, and then I'm going to add it to row 3.
Okay.
And replace row 3 with that result.
Yes, sir.
So what does that give us?
So that'll give 0, 0.
Hold on, let's start at the top. Multiplying 2 times 3, I'm multiplying row 2 times -3 and adding it to 3, so row 1 isn't going to change, right?
No, sir.
So let's get that out of the way.
Yes, sir.
All right. Row 2 isn't going to change. I'm not doing anything to row 2. I am multiplying row 2 by -3, but I'm going to add it to row 3 and then replace row 3.
Yes, sir.
So row 2 stays the same. Okay, now what do I get in row 3? I get multiplying row 3 by 2. Still gives me a 0 there, and then replacing row 3. So I'm multiplying it by multiply row 2 by -3 and add it, gives me a 0 there.
Yes, sir.
Multiplying row 2 by -3 gives me a +3. Adding it gives me a 0 there.
Oh.
And finally, I get a 0 there. In other words, I have to apply it to all the numbers that are on the right side of that vertical bar.
Yes, sir.
Okay. Now, normally, with a beginner's problem, this right there would be a 1. In other words, I would keep going. But I spent 10 minutes trying to make that a 1, and you can't do it. There's no way to turn that into a 1 without affecting the other 2 important ones, which are that one and that one.
Yes, sir.
So it leaves it to be 0, and that last row actually tells you a lot. It tells you there's infinitely many solutions just by its existence. And
yes, sir.
If you want the rationale behind that, you get, well, what's x plus y minus, hold on a second, just a second.
So if you get a row that's all zeros, there are infinitely many solutions.
Well, I didn't know that until doing this, but there's two types. There's infinitely many, and then there's no solution. Notice the no solution does have a number on the right side, which says 0 equals 1. That's never possible. That's when you use no solution. Okay. If you look at this one over here, you notice you have zeros across the bottom, and that probably is the immediate clue that you have infinitely many. But if I look at that row that I have, what does that say? That says x equals, after doing the algebra, in other words, it says x minus 2z equals, hold on a second. Somehow that is true and this is true. Okay, I can see where I get the y equals z, right?
Yes, sir.
And I can actually see where x equals -1 plus 2z, because my final matrix, I don't think I did this step. No, I didn't. Let's make sure we do this step. Hold on, let's back up.
All right.
Told you this was extremely complicated, and it is.
Yes, sir.
Once you learn it, you never have to use it again because they let you use calculators at that point.
Yes, sir.
However, if they're going to insist, so we have this matrix at the bottom, and I'm still trying to turn it into a normal looking matrix. So my next goal, and perhaps this shouldn't be, because maybe seeing the third row being all zeros should be my flag that this has infinitely many solutions.
Yes, sir.
Okay, but I didn't see that yet. So my next goal is I'm going to try to turn each of these into 0. Because then I'll have all the solutions. All right, so here's what I did. I took row 1 minus row 2 and replaced row 1.
Okay.
And this is what I got. I hope my math is not correct here. I'm pretty sure it's not. I mean, I'm pretty sure it is correct. So I got a 0 where I was trying to.
Yes, sir.
Now I got 4 zeros across the bottom, as I had before. In other words, I haven't made much progress. Going from this step to this step didn't accomplish anything.
Yes, sir.
Okay, but now it allows me to say quite a bit. First of all, if I look at that row, that's y minus z equals 0. So y equals z. Do you see why that is? In other words, that's coefficient for z. So
yes, sir.
1y minus 1z equals 0, which means y equals z.
Yes, sir.
This row means x minus 2z equals minus 1. Which means x equals minus 1 plus 2z. Now notice I have two equations, but I have three unknowns. I have an x, a y, and a z. And whenever you have one more variable than you have equations, it's infinitely many. For example, here in the middle of the screen,
Okay.
In the middle of the screen, if I say x plus y equals 10, that's one equation only, but it's got two variables. And there are infinitely many solutions. X could be 1, y could be 9, x could be minus 1, y could be 11, and now you can see that there's infinitely many.
Now, is that just if there's one more variable, or can it be if there's any?
Well, or two. I mean, you're never given that problem. I've never seen a problem where they give you 5 variables and 3 solutions, but that's going to have infinitely many also.
Yes, sir.
I think. I mean, I'm not 100% sure, but it's got to be. Because whenever you have one more variable than you have equations, you have infinitely many. And that's what we have here. In other words, we have one equation, 2 equations, but we have 3 variables, x, y, and z.
Yes, sir.
So, if you put it into your calculator and you get this reduced row echelon matrix, which is this.
Okay.
There's the one equation, there's the second equation. 2 equations, 3 variables. Now, perhaps because we have zeros along the bottom row, we don't need to do this. We instantly know that there's infinitely many. And that's my guess, is that that's all we need to know. In other words, once the calculator spits out the bottom row full of zeros, then it's pretty safe to assume you're going to have infinitely many.
Yes, sir.
As opposed to this one, where we have 0, 0, 0, but then we have a number. Well, what that's saying is 0z equals 1, which is impossible because 0 times anything is 0. So this can't possibly be true. After they've reduced it, notice they haven't reduced it all the way. They still have numbers in these spots right here.
Yes, sir.
Well, the fact that you got 0, 0, 0 equals 1 would be the same solution. Let me give you an example of that. X plus y equals 10. X plus y equals 9. Subtract the 2 equations, you have 0 equals 1. Possible, no solution. Whenever you get one number equal to another number, that's impossible. So that tells you there's no solution. So impossible, no solution. Too many variables, not enough equations means infinitely many.
So let me just make sure I got all that. Let me just make sure I understand that. If you basically do the systems of equations in the matrix and you get an untrue statement like 0 equals 1, there's no solution.
Yes.
And if you get a row that's all zeros, or basically 2 equations with 3 variables, depending on the matrix, that is, it's infinitely many.
Yes, that's a good way to look at it. And I do believe that's always going to be true. If you have all 4 zeros, you're going to have infinitely many. And if you have all 3 zeros and a number, then you're going to have no solution.
Yes, sir.
Okay. So, having learned all of that, they're never going to ask you to do that other than once to test your ability to do it.
Yes,
Every
sir.
time after that, they're going to have you input it into your calculator. And do you know how to do this in your calculator? In other words, how to produce that and how to produce that. That wasn't done manually. That was done from somebody's calculator.
What? One of them, the one on the left, is done manually, or?
No, I think both of them were done on a calculator. Because it says using your calculator, write the matrix in reduced row echelon form, which is that. It says
Yes,
the same
sir.
instructions on the other. The only reason I did it
Yes.
manually is because that's the tough part. It's tough to do manually. It's not tough to do on your calculator once you do it once. Now, it actually is tough to do on your calculator, and to the point where you actually have to input these things as separate matrices. In other words, when I input it like this, on your calculator, you have to put that as one matrix, that 3 by 3.
Okay.
And then I think, last time I looked, I did this on YouTube. In other words, I watched a 3-minute YouTube video that told you how to do it.
Yes,
And
sir.
I believe you input that as a separate matrix, and then you request it do a row echelon matrix for you.
Huh.
Now, I'm not even 90% sure of that instructions. And what I would suggest is that whenever you have a calculator question, you have a TI-84, right?
Yes, sir.
Whenever you have a calculator question, go to YouTube and type RREF TI-84 or space TI-84. And it will immediately show you a number of really, really short videos that show you how to do it on that calculator.
Yes, sir.
Show you every step of the way. Now,
Yes, sir.
I hate to give that as tutoring instructions, but to be honest, I just don't ever do this. I don't remember the exact way. In other words, if you put a gun to my head and said, you have to do this, I'd go to YouTube right now and do the same thing that I'm recommending you do.
Yes, sir.
And I think they'll recognize RREF. If they don't, say row echelon format matrix.
Yes, sir.
Matrix in row, reduced row echelon format. And what they'll do is basically give you the instructions that I just gave you. I'm 90% sure that the first instruction is to input that matrix.
Yes, sir.
The second instruction, I believe, is to input that matrix, but it might just be, yeah, it has to be that. And then basically what you do is you put the two together with the proper instruction. And the proper instruction is probably something like this. It's coming back to me a little bit. And you're inputting reduced echelon between matrix A and matrix B. The command is something like that. But you have to first put in the matrix that's the 3 by 3, and then you have to put in the matrix that is the 3 by 1.
Yes, sir. We have a, I think I'm trying that. We have a matrix.
Go ahead and try it right now and make sure you get this answer that's on the lower left. Right there.
All right.
Yeah, it's easy enough to do that it's worth having you do it while we're talking about it. So all you got to do is duplicate that down there, and you will have done it right.
Yes, sir. Okay, reduce short form. Okay, I think maybe this is just able to do it a different way. I was able to enter in the entire 3x4 and put that into RREF.
That is a different way. Because when I looked it up, you had to do it in 2 different steps. So they allowed you to put in that and then that following it?
Yes, sir.
And it gave you this down here on the lower left?
Yes, sir.
Perfect. Perfect. So you know how to do it in your calculator. That's the most valuable thing you learned today.
Good.
Because even these questions ask you to do it on your calculator. They didn't ask you to do it manually. But nonetheless, I believe that it's important to know how to do it manually.
Yes, sir.
All right. Find the determinant of the coefficient matrix. Coefficient matrix is this matrix right there. I assume you know how to do that?
Yes, sir.
Okay. Find the determinant of this coefficient matrix.
It's going to be the same process.
So let's, hold on. What conclusion can you make about the determinant of the coefficient matrix of a system of equations that has either no solution or infinitely many solutions? And so my guess is the determinant's equal to 0.
Okay.
Since that's what that says. In other words, if you were to go through it's clear to me now that that's what's going on here. In other words, when somebody found the determinant, they got it to be 0. When they found this determinant, that came out to be 0. So a determinant of 0 doesn't tell you exactly what's going on, but it tells you one of 2 possibilities.
Oh, okay.
It's either infinitely many or none. It's not a unique solution. A unique solution means you have an exact solution for X, Y, and Z.
Okay.
Okay, and the determinant will never be 0 when you have an exact solution.
Yes, sir. And this is just for the coefficient matrix?
Yes. Notice that says the determinant of the coefficient matrix, the coefficient matrix, the coefficient matrix. So that's what really matters, yeah.
And does it only work like that because the coefficient matrix is a square matrix in this case?
Don't know for sure, but you can see what happens when you have a row of zeros is the determinant's going to be 0, whether it's 4 zeros or 3 zeros.
Yes, sir.
Remember what the determinant is. It's that times the next one with a 0 times the next one with a 0 minus that has a 0 minus that has a 0 minus that has a 0. So when you have 3 zeros in your bottom row, that absolutely means that the determinant is 0. Has to be. Because all 3 of these numbers end up multiplying something, and when you multiply something by 0, you always get 0. So having 3 zeros in your bottom row means the determinant is 0. But in these 2 problems, we had 3 zeros in both of them. So you can't tell by just those whether it's infinitely many or none. But apparently, I do believe if the thing to the right of the bar is a number, it's none. And if it's a 0, then it's infinitely many. And I think that's got to be true. I just got to believe that's true.
Yes, sir.
So if you can manage to get it in your calculator, you can tell instantly by looking at it whether it's unique, which is another way of saying trivial, I think. The next page has the word trivial on it, and I think that means unique. Shall we go to the next page? Are we done with this one?
Yes, sir.
All right. It says, find all values of k such that each system has only a trivial solution, that has to be unique, and an infinite number of solutions.
Yes, sir.
All right. So, first of all, multiply these two matrices by one another. And the reason we can is this, hold on, let me write it above here. This is a 2 by 1, starting always with the rows. Excuse me, 2 by 2. And this is a 2 by 1. Long as those two inside numbers are the same, you can multiply them.
Okay.
In fact, the only time you can multiply them is if those two numbers are the same. You can multiply a 2 by 1 times a 2 by 1.
Yes, sir.
Okay? All right. So it's the same in this case. Let's go ahead and multiply it together. What do you get? First of all, what are you going to get? We're doing a 2 by 2
okay.
times a 2 by 1.
You're going to get a 2 by 1.
Yeah, you can only do it if these two are the same, and the result is always that.
Okay.
So the result is always the outside. You're going to get a 2 by 1. In other words, we're going to get something that looks like that. And indeed, that is a 2 by 1 in the answer. So let's do the multiplication. What do you get?
That's going to be 2x1.
2x sub 1.
2x sub 1 plus, hold on, let me make sure that I'm doing this right. You take the column by the,
yeah, here's the way I look at it. You can look at it in many different ways. But I take this matrix on the right, x sub 1, x sub 2.
Yes, sir.
I rotate it by 90 degrees to the left.
Yes,
and
sir.
I place it on top of the first row. And that gives me this.
That's right. And then the second row is going to be 3x sub 1 plus kx sub 2.
And that's equal to 0, and that's equal to 0, because they're telling us that that matrix is 0, 0.
Yes, sir.
Okay. So, if we try to solve this, we can eliminate the x variable if k is 3/2. Well, let's talk about this for a second.
Yes, sir.
Let's go over here. X plus y equals 10. 2x plus 2y equals 20.
Yes, sir.
That is not two different equations. That is one equation plus another equation that was merely multiplied by 2 on both sides.
Okay.
So I know that that's really only one equation, two variables, infinitely many solutions, automatically.
Okay, because they're the same equation.
Exactly. In other words, the only time you're going to get a either a trivial solution or no solutions is if you have a second equation that's different. Has to be different. Okay?
Yes, sir.
So, the way my logic on this thing went was they're looking for let's find the infinitely many first.
Okay.
Well, I know if equation 2 is merely a multiple of equation 1, I'm going to have infinitely many.
Okay.
Well, what if k is equal to 3/2? Then equation 2 is just 3/2 times equation 1.
Yes, sir. Because that makes them the same equation, because they're the same ratio.
So when k is equal to 3/2, you automatically have infinitely many.
Okay.
Because it's the same equation.
Yes, sir.
Okay, so now hold on a minute. So if I subtract, let's see if we can solve for the trivial solution.
Yes, sir.
It's the best way to do it. I actually take that back. I'm just going to arbitrarily subtract 1 from 2.
Okay. So that would be x1 plus k minus 1 x sub 2.
Very good. So I know that k cannot be 3/2 because 3/2 represented the infinite number of solutions.
Yes, sir.
But notice if, wow, just realized I don't know how to solve this. The trivial solution.
Is the trivial solution when all the constants are equal to 0?
Here's what I thought was the case. That as long as k is not equal to 3/2, in other words, if k is any number but 3/2, you have a real solution because now you can solve that. Let's say make k equal to, hold on, let's extend this thinking. Let's let k equal to 2.
All right.
Then I would have that plus x sub 2 equals 0, which means x sub 2 equals minus, x sub 1 equals minus x sub 2. And as long as x sub 2 is equal to minus, or excuse me, x sub 1 is equal to minus x sub 2, then this should be a real solution. Now, some reason I questioned this when I just started talking about it. Hold on, let's give this a little bit more thought here. Let's test out my hypothesis.
Okay.
In other words, if k is equal to 2, does this give me a solution? So let's see. So now I have 2x sub 1 plus x sub 2 equals 0. And I have 3x sub 1 plus 2x sub 2 equals 0.
Yes, sir.
Now let's see if that gives us a unique solution. I don't think it does. Let's see. I can subtract 2 minus 1 to get x sub 1.
So x sub 1 is going to be equal to negative x sub 2 in that case.
Right. Which is what I got before. Now the question is, that to me is not a trivial solution because x can be any x sub 1 and x sub 2 can be a lot of different things. In other words, I assume a trivial solution gives me a solution for x sub 1 and x sub 2. And this gives me infinitely many. In other words, x sub 1 could be 10, x sub 2 could be minus 10, x sub 1 could be 8, x sub 2 could be minus 8. So I've got lots of different solutions, as I would expect because I have 2 variables and only one equation. So I'm not sure what to do with that. Let me think for a second. We already know that if k is equal to 3/2, I have infinitely many solutions.
Yes, sir.
And it appears that if k is equal to 2, I have infinitely many solutions. And I suspect if k is equal to 3, I'm going to have infinitely many solutions. So I'm not sure I know how to do this one.
I think the trivial solution might
not be a unique solution?
I don't think it's this. I'm not entirely sure.
I wasn't sure when I saw that. I'm not used to that terminology. Terminology that I've always seen is no solution, a unique solution, or infinitely many. Those are your 3 choices. So what does this mean?
What trivial solution, I think what they described it to me as was, I guess it's kind of like what they have shown. When the coefficients are, basically the solution to it when the coefficients are equal to 0. Or when the constants are equal to 0.
Is a trivial, or I meant k. In other words, is that a trivial solution? Where k is, we already know that if k is equal to minus 3/2, we have infinitely many.
I think in this case it would be the same, minus 3/2, because
trivial means infinitely many.
I'm not sure exactly the definition of trivial solution.
Okay.
But with some of the, because I never got the definition of trivial solution. I just know that it's when the constants are equal to 0, and for some of these examples, I get the answer. The answer was shown to be infinitely many, but it's all in a ratio.
Okay. So, I gotta think that means something different, because otherwise why use different terminology? In other words, if trivial means unique, then he would have said unique, because he uses the word unique in the next question.
Yes, sir.
So it might mean something I'm just not aware of. Well, I tell you what, maybe it will become apparent if we look at B.
All right.
You think we can do B rather quickly? Go ahead and multiply them out. Tell me what you get.
All right, I get x sub 1 plus 3, x sub 2 is equal to 0. 3x sub 1 plus k squared x sub 2 is equal to 0.
Okay.
So
what K, the first thing I would start here, and maybe it's not the best starting spot, but I know I can figure out which one, what K makes it an infinite number.
Yes, sir.
What K makes equation 2 the same as equation 1?
Positive or negative 3.
Very good. Positive or negative. So K equal plus or minus 3 is the infinitely many.
Yes, sir.
And the trivial, I'm not even sure it's worth going through the math because I'm not sure what it even means. So if you have some suggestions, I'm happy to do it, but we might be better spending our last 5 minutes trying to do one of those.
Yes, sir. I think we can do one of those.
Okay. So let's first of all see if we can find a unique solution. That's probably the easier thing to do. In all, we already know what a unique solution is. So what I want you to do, put that into your calculator. Hold on a second. Yeah, your calculator's not going to like that. No. Wow. Determine all values of K. Well, let's look at this for a moment. Well, the only way I can even think to begin is by writing out that matrix.
All right. Okay.
Now, I don't know if I doubt your calculator is even capable of figuring out a K that makes that unique. I mean, I don't know. That's what I say. We're starting at level 8 here. We're not starting at level 3 of reduced echelon matrices. Every other student I've had probably 3 students in 10 years that have even presented reduced echelon, and they're never asked about infinite or no solution. They're always asked to solve it. In other words, come up with the unique solution. These kind of problems I haven't seen them in 40 years.
Wow.
Since college math. In other words, my history is I have a degree in math from Colorado School of Mines 40 years ago, and then 10 years ago I decided to refresh my memory in all of it, but the only thing I refresh is stuff that students give me. And no students give me this. So I may have learned this one time when I was in college, but how to do it now, the way I would go about trying to solve that would be manually doing it. In other words, try to turn that into a 0, turn that into a 1, turn that into a 0, and then turn that into a 0. And then you're going to have K squared minus 5 equals to whatever that becomes. And then you can probably solve for K.
So that, and then you'll be able to figure out for infinitely many as well as.
Right, exactly, you will. In other words, what I can tell you right now, well, no, I can't tell you right now, but after doing work on this matrix, trying to turn it into ones and ones on the diagonal and zeros left of each of those ones.
Yes, sir.
Then I will come down. We're not going to have time to do this, so let's just pretend we did it.
Yes, sir.
And I get something like this. I don't care what's there, or what's there, or what's there. What's important is I have a 0 there, there, and there.
Yes, sir.
And I have numbers over here, A, B, C. If I can turn it into this,
yes, sir,
then I'm going to be able to say that Z is equal to C. Or in our case, some K times Z is equal to C, where C is going to be a number. And then you'll be able to figure out what K makes this thing a 0. And that thing being a 0 is what you need to have either no solutions or infinitely many.
Yes, sir.
So you might be able to make progress on this problem by doing it like that. I see all 4 of these are very similar. So once you learn the technique, you can apply it to all 4 of them. But I honestly don't know the technique. That's what I would start with. I don't know that your calculator is going to help you here. Because it's not going to know what the hell K is. Okay? Now, I might be wrong. You might try doing RREF on this matrix using a variable like K and see what your calculator says. It may give you, it may be able to handle a variable in place of a number. And at a start, it might give you something like that. And that's a lot of information. I tell you there's no solution. Because I got 0 equals K. Unless K could be 0. I suppose K could always be 0. But now you can kind of see that if K were to equal to the square root of 5, that coefficient is 0. Totally wipes out that. So maybe that's the place to begin, where you let K equal to actually plus or minus the square root of 5. And that makes that lower third cell start off equal to 0. But I think maybe you have to get it to this spot first, where that will be some number of K or K squared or something. And then you can figure out what it would take for that to be a 1, what it would take for that to be a 0, and what it would take for this to be a 0 and this to be something other than a 0. So that's kind of what I'm guessing is the way you would solve these. I don't know. You can either ask your teacher what his methodology is for these and go with that. It's probably easier than doing an hour worth of experiments. Although I would certainly give it a shot on doing one of these. Try doing it the way I suggested and see what you get. And if you discover that that works, then you can apply that methodology to that one, and this one. Or you could just ask your teacher to tell you how to do one of them, memorize the methodology, and go, and then you can do the other 3.
Yes, sir.
I don't know what else to tell you. You've exhausted my knowledge on matrices, including reduced row echelon. These are bears to understand. Although it's not so bad if you always can do it on a calculator. It becomes relatively easy to understand when you can do it on a calculator. But figuring out what these coefficients need to be, I don't know. You know, maybe, no, I don't know. I don't know. I would suggest playing around with at least one of them and trying to turn that into a 1, and a 0, a 0, and a 0, and see what you get for this spot right there when you try to do all of that.
Yes, sir.
Garrison, I will let you go, and I will talk to you next Tuesday.
All right.
Here, before I let you go, you sent me a couple of additional papers today.
Yes, sir.
Are those on something other than matrices?
They are. Yes, sir.
Look like word problems. Okay, so we'll be going over those at our next session?
Yes, sir.
Okay, I'll make sure I know how to do them. I don't want to put the time in if there's going to be another set of papers by next Tuesday that we're going to be working on. You understand what I'm saying?
Yes, sir.
I have no problem putting the time in if that's what we're going to be working on next Tuesday. And I will. I'll look at both of those pages and see if I can figure out how to do them. I suspect they won't be easy. Nothing you give me lately has been easy. Okay?
All right.
But it's been fun and educational. So.
Yes, sir, it has.
All right, Garrison. I'll talk to you later.
All right. Have a good day.
You too. Bye-bye.
Bye.